So we are recording. Just a few Zoom basics and etiquette. We ask just to minimize distractions today that you leave your cameras off if possible. You are welcome to turn those back on if you have some questions during the Q&A period with Dr. Hopkins. Let's see, we have enabled live transcripts. So you may be seeing subtitles down at the bottom of your screen. There is an option to hide those subtitles if you would like. So check down, you may see a live transcript button, or you may see the more option to hide subtitles if those are distracting. And we want to invite you to submit your questions using the chat box today. So as you think of them, go ahead and pop them in the chat, and yeah, hopefully we'll facilitate a good discussion. So again, at this time, I'm going to go ahead and turn it over to Daniel Wibke, the president of NCWRA, to officially kick us off this morning. Take it away, Daniel.
Awesome. Thanks, Anna. So I wanted to roll through a few announcements here. We have these forums from time to time, and wanted to just say, I don't know who all's had a chance, but we redone the website a few months ago, and if you haven't had a chance, please check that out. Rebranded a little bit and working on some new offerings and continuing to take suggestions on that. So if you have any suggestions, please feel free to reach out to us either via email. I think some of our emails are on the website on the board, as well as there's a comment section. Also, for those of you who whose memberships may have elapsed, please be sure to renew your membership. Again, this is how we make sure that we send things out on the listservs and can communicate different offerings to you all, whether it be lunch and learns, other forums, workshops, that kind of thing. There are some more forums coming in September and December. We're still working on the subject matter for those, but again, feel free to comment and let us know any thoughts you have, and we will take those into consideration. Again, we can always use some help on different committees. So we have 3 committees here at NCWRA currently. Feel free to email us or comment if you're interested. We have the program committee, which helps to determine some of the subject matters that we talk about and get speakers. Membership committee, which is, discussing different benefits and other strategies that we have and some of the things that we get here at NCWRA as being a member. And then communications committee, that's mostly helping to spread the word about our organization, the different events and that sort of thing. So again, feel free to reach out to myself, one of the other board members, or put a comment in through the website. And the last thing, I'm very excited to announce this, is that in 2023, Raleigh-Durham will host the AWA National Conference. So there will be more to come on that, but we've been working in the background a little bit, trying to figure out where it'll be, venues, that kind of thing. But as of right now, Raleigh-Durham will be hosting the 2023 AWA National Conference. So with that, we will get to today's speaker. All right, so today we have Krissy Hopkins. So Dr. Hopkins' presentation will take us on a journey that explores how rainwater moves through our neighborhoods. She will discuss how neighborhoods in Clarksburg, Maryland were designed to incorporate engineered and green stormwater infrastructure practices to minimize the impacts of development on local streams. Monitoring data reveal how the streams fared 15 years after development. Stay tuned to learn about the ecological, hydrologic, and geomorphic changes that have taken place in these neighborhoods. Dr. Krissy Hopkins is a research scientist at the US Geological Survey in Raleigh, North Carolina. Her research focuses on understanding the impacts of urbanization on rivers and streams and ways that green infrastructure can be used to minimize the impacts of urban and suburban development. So with that, I'll turn it over to Dr. Hopkins, and I hope you all enjoyed today's.
Great, thanks, Dan. Can everybody hear okay? Can you hear me okay, Dan? Good. Hopefully you can't hear my neighbor cutting the grass. Yeah, okay, I'll just assume that everything's good. Thanks everybody for coming. Excited to talk to you today about this long-term monitoring project that I've been a part of for the last 5 years. I just want to recognize a team of people that I work with on this project at USGS. We're a diverse group and a younger group, so it's a really fun team to work with, and just want to recognize my coworkers who have helped with various parts of this project. Just a little roadmap of what I'm going to talk about today. Start with a little brief history of urban water systems and how they've changed over time. And then just some highlights from monitoring that we've been doing in Clarksburg, Maryland. I'm going to talk a little bit about changes to streamflow and the hydrologic regime in neighborhoods, a little bit about water quality, and a little bit about ecology. So actually I'm skipping the geomorphic section. I decided to add water quality in there instead last minute. So if you're interested in geomorph stuff, you can shoot me an email and I can send you some highlights. And then just kind of wrap up with urban stormwater futures and some issues that are kind of emerging in the future. So urban water systems have changed over time. This isn't surprising to anybody, depending on what city you're living in. The water system and the way the pipes that connect our roads and houses to our rivers and streams vary depending on when our neighborhood or our city was built. If you look at really old cities, they have things like combined sewer systems that send stormwater and sewage into the same pipe, and then that water overflows into rivers and streams during certain rainfall events. Typically, newer cities don't have those combined systems. They have just a separate stormwater network and a sewer system, and those pipes are designed to just drain stormwater directly to waterways, get water out of cities quickly so that we don't have flooding problems. Then starting in the 60s, cities that have wastewater infrastructure started to become common in cities, and we built wastewater treatment plants to start treating that wastewater instead of just sending it directly into streams and rivers. So we can think of these that area as kind of a waterway city, where we started to recognize that sending waste directly into our rivers and streams is not a great idea, so we should treat it in some way. And now we're kind of moving more towards this water sensitive city, a city where we integrate natural infrastructure into the landscape to try to treat stormwater in a way that provides multiple benefits, not just treating it at a facility, but providing vegetation and habitat and green space for people that live within the city. So what happens when we drain our cities? When we just put these pipes in to drain the water quickly, what does that mean for our rivers and streams? As part of my dissertation work, I looked at how stream flow, various aspects of stream flow change as you look at rural watersheds and move towards more urban watersheds. So we looked at 10 years of stream flow data and tried to look at how those aspects of the stream flow regime vary across the gradient of urbanization, and look specifically at metrics that were ecologically relevant. So things like the magnitude of flow events, the frequency of flow events, and the length of those events. And today I'm just going to show you a little bit of results from looking at the frequency of events. So just counting the number of high flow events there were in each of these watersheds over time. So there's decisions that we make and the way that we build our infrastructure in cities results in certain characteristics of the stream. So we looked at these counts of high flow events. So the y-axis here is just the average frequency of a high flow event, the number of times the flow gets to a certain level across each watershed. So each point is one watershed within a city. And then the x-axis here is just road density. So it's a proxy for urbanization, kind of a gradient from rural to more urban watersheds. And then the 9 cities that I looked at are listed in the top left corner there. And Raleigh was one of those cities, but there was one city that I looked at in North Carolina. And you can see how all these different cities, watersheds in these cities across these gradients vary, and kind of see a similar pattern of increasing in the number of high flow events as you go from rural watersheds to more urban watersheds across this gradient. But you can see the cities kind of cluster in these brown dots versus the blue dots or blue squares. So just think about what the difference is between these 4 cities in the brown dots versus the 4 cities in the blue squares. What are the differences between those cities that might lead to this trend where you have more high flow events in the cities that are brown versus the blue cities? And if we look at where Raleigh plots there, here's just some streams for those folks who are interested in, familiar with streams in Raleigh. Rocky Branch was one of the streams that had a higher frequency of flow events. Same thing with Marsh Creek and Walnut Creek. But if we just look at these watersheds that have road densities of about 10 kilometers per square kilometer, you can see a lot of variability here. So if you think about where these cities are that have fewer events, Boston, Detroit, Portland, St. Paul, one obvious difference that drives these patterns is rainfall amount and type. So cities that have more snow melt dominated flow regimes versus cities where we don't have a lot of snow down in the South here, like Atlanta and Raleigh. They're going to have more events per year. But also landscape features can act as hydrologic buffers. So if we look at just an aerial view of 4 of these cities that I looked at, you can think about things like lakes and wetlands. It can act as hydrologic buffers to store stormwater during rainfall events, and that can reduce the frequency of those really high flow events. But also topography. So here's just a snapshot of Pittsburgh, which is very hilly. So I'm from Pittsburgh. And this is a view of Mount Washington, just up slope of the rivers in the city. And if you have very steep landscapes, you're going to have water moving much more quickly through a watershed than a flat city like St. Paul, where water will move more slowly. But just as the landscape can act as a hydrologic buffer, so can stormwater features. So there's all different types of stormwater features that we can put in a watershed. But the real question is, well, how many and what kinds of stormwater features should we be putting in our cities? And in some places, we kind of adopted the old infrastructure that was there, but when the city was first constructed, or maybe there's not even any stormwater infrastructure, just having storm drains that drain directly to rivers and streams, and no sort of stormwater management facilities to manage that water. So this is when we think about like our neighborhoods and how they were developed. If you just look at an aerial image of a neighborhood, you can kind of pick out some differences here. So here's just a generic neighborhood, and we can look at when the houses were built in that neighborhood and think about the types of infrastructure. So here's a neighborhood that was built in the 30s, where you have larger lots and fewer streets. And then, during post-World War II suburbs, we started building streets on gridded patterns and denser houses. And then we started putting in cul-de-sacs. So people wanted quieter streets. And you can just look at the landscape here and think about, what types of stormwater features might vary within this really small neighborhood, just due to when houses were built within this section of a tiny part of a city. So neighborhood age often determines the type of stormwater plumbing that we have in our cities. Older cities have no treatment of stormwater, it just goes right into rivers and streams. And then newer neighborhoods typically have detention or retention ponds, large facilities that treat a lot of area, and we're kind of moving away from that towards having fewer facilities, more facilities that are smaller to treat smaller drainage areas, things like fire retention rain gardens and tree box filters and things like that. So the question is, well, what's the best thing to do? What's the optimal solution to our stormwater problems? And it's a kind of a loaded question. There's many solutions to a problem, but kind of what happens when we shift from using a few large centralized facilities to a distributed network of many small facilities across a watershed. So this comparison is what I've been working on for the last 5 years, looking at some monitoring that we've been doing in Clarksburg, Maryland. And just to give you a snapshot of what the study area looks like, here's an aerial image of the landscape in 2002. So it was mostly agricultural land use. And then in 2018, you can see all of the subdivisions that were built in this area. And this is located north of Washington, D.C. So it's a growing suburb of Washington, D.C., located in the Piedmont of Maryland. And we have a forested reference watershed, that's a county park, which is this watershed to the north, and an urban control watershed to the south here, which has large centralized detention and retention ponds as the main stormwater control practices in the watershed. And then these 3 treatment watersheds that went from agriculture to suburban development during the monitoring period. So we've been looking at how these treatment watersheds have changed over time, and also how they compare after they were developed to these control watersheds, the forested control watershed and the urban control watershed. So we've been looking at tracking when that development happened, and each of these 3 watersheds developed in kind of successive time periods. So the treatment 1 watershed transitioned from agriculture to suburban development in the early 2000s. So we have these 3 time periods when it was agriculture versus when a lot of construction was happening, land grading, and when the county and the developer instituted sediment erosion control facilities. And then when development was completed is this last bar here showing development ended in this watershed in about 2011. And then when that development ended, they started developing this other watershed, treatment 2, and development ended in that watershed in about 2016. And then treatment 3 is currently still being developed and constructed. So I'm going to focus mostly on these 2 treatment watersheds and show you just a little bit about the treatment 3 watershed. So when we zoom in and look at the types of stormwater facilities within this area, we can see that there's a pretty high density of stormwater practices in each of these 2 watersheds. So the dots here show different stormwater facilities, and then the red lines here show you the roadside swales. So instead of having a storm drain, the neighborhood has kind of a series of swales that go next to the driveways that drain the water to a storm drain at the very bottom. So the treatment 1 watershed is 33% impervious. It's mostly single family detached houses compared to the treatment 2 watershed, which is the higher level of impervious cover. It has 44% and a mix of single family homes and townhouses, so kind of denser development and a higher density of stormwater practices, which are smaller facilities, things like tree box filters and infiltration trenches and berms that manage a much smaller drainage area compared to the treatment 1 watershed. So going from a pretty high density of stormwater facilities in treatment 1 to an even denser network of stormwater facilities in treatment 2. And what's interesting also is that the stormwater facilities are arranged in treatment trains. So we zoom in on that little area, this one section, you can see that this part of the neighborhood drains to a water quality filter that drains to a sand filter, which drains to a dry pond, and then the dry pond eventually discharges into the stream. So each of these little sections in the neighborhood has a slightly different arrangement of BMP redundant stormwater treatment within this neighborhood. We can also look at a kind of breakdown of how much storage is provided in the different types of facilities. So even though there's a really high density of facilities in this watershed, most of the storage is actually in the dry ponds and sand filters rather than the smaller BMPs that are upstream. So in treatment 1, about 90% of the storage is provided by the dry ponds and sand filters when you look at the actual capacity of each of these different types of facilities compared to the treatment 2 watershed that has more storage sort of distributed upstream of the dry ponds and sand filters. So about 63% of the storage in this watershed ends up in a dry pond or a sand filter. So as part of this project, we've been looking at various aspects of watershed health and stream health. So we've been looking at how these characteristics, the Benthic community, water quality, geomorphology, and hydrology change as these watersheds transition from agriculture to suburban development. So like I mentioned, I'm not going to talk about geomorphology today. I'm going to focus on these other 3 aspects and start off with hydrology. So looking at how the flow regime has changed after a development and during development in these different watersheds. So when we talk about the flow regime, I'm going to show you some results today from thinking about things like how much rain does it take to initiate a flow response in the stream, how do peak flows and runoff amounts change, and also how does base flow change in these watersheds. So to do this, we had to identify storm events, individual storm events, and link them to rainfall events. So we took 5-minute Streamflow data for a 14-year period and identified each flow event during that record and separated out stream flow, runoff from base flow to identify each of these individual events. So we identified over 1,000 events in each watershed and linked it up to the associated precipitation events. We knew how much rainfall fell and then what the stream flow response was for that event. And this looked at the treatment 1 watershed and treatment 2, and then those 2 control watersheds. So we look at how much rain it took to initiate a flow response in the stream. And the forested watershed, like you might expect, it took a lot more rain to initiate a response in the stream than the urban control watershed that had that centralized stormwater control. So it took 11 millimeters of rain in the forested watershed to have a flow response, and only 5 millimeters of rain in the urban control watershed. So this is showing you the depth of precipitation on the X and then the probability of a stream flow event on the Y. So if we just look at like 75% probability that there would be an event, if you just go down here for the urban watershed, you can see that's about 5 millimeters, and you go down in the forested watershed, it's about 17 millimeters. So the question was, well, what happens in those treatment watersheds? We have some data from the treatment 2 watershed before development, and it was pretty similar to the forested watershed, about 17 millimeters of rain to initiate a flow response. And then we can look after development in the treatment watershed. You can see that they kind of shift, especially treatment 2, this blue line shifts closer to the red line. So it takes less rainfall to trigger a flow response after development. So 17 millimeters compared to 12 millimeters of rain. But the treatment 1 watershed is still pretty similar to the forested watershed, even after it's developed with 33% impervious cover. And if you're not used to millimeters, here's those numbers in inches. So about half an inch of rain after development in the treatment 2 watershed to initiate a flow response, and about 0.6 inches in the treatment 1 watershed. So we can think about, well, why is this important? This tells us something about the frequency of disturbances that the critters that live in the stream experience. So the more, the less rain it takes to initiate a flow response, the more disturbance you're going to have. And we also looked at the amount of runoff that it takes in these watersheds, and we can look at different scales. So I showed you those treatment trains. If we look at just kind of a curb and gutter section of the neighborhood, so kind of the street scale, the curb and gutter neighborhood had higher runoff yields or similar amounts of precipitation than a small street scale neighborhood with this distributed stormwater control. So especially for events that were small, so like less than 20 millimeters of rain, the distributed neighborhood had less runoff than the curb and gutter neighborhood. And then we kind of scale up and look at the watershed scales. When you combine multiple streets together, there was more runoff from the centralized stormwater watershed and the treatment 1 watershed, which actually has the should say treatment 2 watershed that has that distributed stormwater control, but the higher density and the smaller practices. As you get to larger and larger rainfall events, those actually end up having higher runoff amounts than the urban control watershed or the forested watershed. We can also look at the magnitude of those events. So what's the peak flow at that stream over time? And when we look at peak flows, and these are normalized to drainage area, we see that for smaller events, these box plots just show the distribution of peak flows for events that were between 1 and 10 millimeters of rain. You can see that those treatment watersheds are similar to the forested watershed, and that the urban watershed rain control with the centralized stormwater management have higher peak flows. But then as you go to larger and larger precipitation events, peak flows increase, and they're kind of in between the forested and the urban control site for medium-sized events. But then for larger events, the treatment watersheds don't replicate forested conditions. They kind of transition closer to the urban control site. We can also look at change over time within one watershed, since we have sort of a before snapshot and an after snapshot in this treatment 2 watershed. And these plots here just show those same variables, peak flow and runoff yield, but instead show you each individual rainfall event before, which is the yellow, and after, which is the blue. So across this watershed, we see an increase in event duration, an increase in peak stream flow, runoff yield, and also runoff ratios. And we can look at an individual response before the watershed was developed, and then after. This is hydrograph for similarly sized precipitation events before the watershed was developed and after. And you can see also differences between when antecedent conditions were dry, so when there was more storage in the facilities, versus when there was wet conditions previously in the previous 2 or 3 days. We can also look at baseflow changes in these watersheds. So distributed stormwater control. So a lot of these practices focus on infiltrating the stormwater into the ground, and saw an increase in baseflow across the time period. In some of these watersheds, even in the forested watershed over time. So the boxes here show you the construction period of each watershed, and the baseflow yield, annual baseflow yield over the last 15 years. So you can see the box here in treatment 2, you can see an increase in baseflow, and also in treatment 3, but no increase in the urban control. And then we can normalize those baseflow yields to the forested site, and see that in a lot of these treatment watersheds, there was an increase in baseflow relative to the forested site during construction or shortly after construction. But in treatment 1, where we have the most post-monitoring data, we can see that increase in baseflow is kind of a temporary thing. You see baseflow declining in that watershed relative to the forested site after development ended. So just a summary of how distributed stormwater control does it maintain hydrologic function. We found that it can attenuate peak flows and runoff volumes, especially for smaller rainfall events. So those events that are less than 20 millimeters. But the storage capacity of the stormwater facilities really matters. We can't build ginormous stormwater detention ponds to hold water in some of these neighborhoods. This pond is pretty big, but it's multifunctional here. They use it for also a walking trail and kind of green space for the neighborhood. But you can only build so much capacity. So that capacity really matters, and where the capacity is placed on the landscape seems to matter. We also found an increase in base flow, but that increase appears to be temporary. So we were able to look after development in those other two watersheds. We see a similar pattern where there's an increase during construction, but then base flow declined. Does that pattern happen in these other two treatment watersheds? And then more distributed control isn't necessarily better if you have more impervious cover. So even though that one watershed had a really, really high density of stormwater practices, there was a lot more impervious cover in that watershed also. So perhaps the overall storage capacity is lower, even though you have more facilities. They're just smaller facilities that are upstream. So just thinking about changes in water quality, I looked at patterns in nitrate. So in the treatment 1 watershed, we had some longer term data for nitrate in the surface water, which is the blue circles here, and the groundwater, which is the white triangles. You can see that nitrate concentrations actually declined by half in the groundwater and to some extent in the surface water in the treatment 1 watershed over the course of development. So here's when construction happened and kind of ended in 2010. But it's higher than the urban control site, which is the diamonds, and the forested site, which is the squares. So if you know anything about the Piedmont in Maryland, you can think about legacy nitrogen and the timing of agricultural conversion. So when the urban control watershed transitioned from agriculture to development was in the 80s, whereas the treatment 1 watershed development occurred in the 2000s. So just think about how much time there was between when all that nitrogen that's hanging out in the soil was able to kind of be used up and flushed out in the urban control watershed compared to the treatment watershed. And even the forested site has high nitrate concentrations, so 1 milligram per liter for an urban control site. That watershed also had an agricultural history. The whole watershed was agriculture in like the 1920s and 30s, and now it's just regrowing into forests. The other thing that's changed in the treatment 1 watershed is that during construction, a lot of the soil was removed or moved around in the watershed. So 81 centimeters of earth removed for every 1 square meter of watershed area in this watershed. So think about what that means in terms of removal of some of that legacy nitrogen in the soil when the landscape was reconfigured to allow for the construction of this neighborhood. So changes in nitrate concentrations, this is baseflow nitrate. It's not looking at during storm events. So baseflow nitrate patterns are more driven by the agricultural legacy than the stormwater facilities themselves, and also a reduction in fertilizer inputs from the agricultural practices previously. You can also look at sediment. So this is thinking about during storm events, what happens to sediment. And it developed a surrogate model to estimate sediment export for individual storm events in 3 of these watersheds: the forested control, the centralized stormwater control watershed, and the treatment watershed over time, and looking at those individual events, and can see that the distributed stormwater control watershed actually had less exports. So this is 24 storms where we had enough data to develop, to apply this surrogate model. 24 storms where when you add up all of the sediment that was exported for all of those events, the treatment 1 watershed had less export than the forested watershed, but that's because for these really large events, the forested watershed actually exports a lot of sediment. When you compare the distributed stormwater treatment watershed to the urban control site with the centralized stormwater control, that watershed also had less export, and most of it was dominated during these large storm events. And when you look at export in the stream versus what's coming out of those stormwater facilities, it's actually likely that stream bank erosion is contributing a lot of that sediment rather than sediment upstream of those facilities. Because we have a sand filter and dry pond, a lot of the sediment is trapped in those facilities, but you still have those high peak flows, which is resulting in a lot of stream bank erosion in the watersheds. We can also think about specific conductance in this watershed. So we can look at patterns in specific conductance over time, and specific conductance is increasing to different degrees in these treatment watersheds over time as well. So the treatment 1, we're seeing the highest increase in specific conductance, 32 microsiemens per centimeter per year increase in that watershed since development happened, compared to the other treatment watersheds, which have a lower rate of increase. So these increases in ion inputs are likely due to the increase in impervious cover and also road salting, increasing salting the roads in these watersheds, which is a stressor that's not necessarily targeted for these stormwater facilities, and they weren't designed to capture salt and treat salt, and an increase in ions. So distributed stormwater control, can it maintain water quality? It can reduce nitrate in the stream, but those differences are mostly related to sort of the legacy nitrogen. And when you look at total export, the export actually remained about the same because of that increase in baseflow. So while concentration went down, baseflow went up. Therefore, overall, the export of nitrate in that treatment 1 watershed remained about the same over time. Results indicate that it can reduce sediment inputs to the stream, but in-stream sources dominate sediment export during those large storm events, and those peak flows are what are really driving that sediment mobilization in that watershed. Distributed stormwater control, not necessarily, but development itself can actually increase ion loads. So we saw an increase in ion loads, but that's more due to impervious cover rather than the stormwater facilities themselves. And then lastly, and maybe most importantly, what happens to the Benthic community in these watersheds? That's what we're really interested in. What happens to the health of the community that lives in the stream itself? So the county has been monitoring the Benthic community in these watersheds going back to the 90s. So we were able to take the data that the county's collected and try to synthesize it and try to understand what's going on, coupling with changes in land cover in these watersheds. So I'll show you a series of plots that look like this, where you have sampling year on the bottom and then an index of biotic integrity for the Benthic macroinvertebrates that were collected on the Y. So lower scores indicate poor biotic integrity, and higher scores are better biotic integrity. So we can look at the 2 control watersheds, and the forested site remained in kind of good to excellent condition over the whole time period, whereas the urban control site, that's that older centralized stormwater management, remained in fair to poor condition over the course of the monitoring period from 2004 to 2018. And then we can look at the treatment watersheds before development or just during the start of development, and they were both in good condition in 2005, so before development happened, and when development was just starting to occur in the treatment 1 watershed. And then you can see that during large-scale land clearing, the biotic community dropped to fair in the treatment 1 watershed and remained in good condition in the treatment 2 watershed because it's still, in the same land cover it was in before. And then after development ends, the stream actually rebounds to good condition based on IBI scores and kind of remains that way. And as the treatment 2 watershed starts to become developed, so a lot of large scale land clearing, we see declines in the Benthic community in that watershed. It drops to fair during construction and kind of remains that way after development has completed, and the watershed is now a neighborhood, whereas the treatment 1 watershed has kind of fluctuated to some extent but remained in good condition after development. So IBI scores tell us something, but they can also be a little bit deceptive in what they are telling us. So we can dive down a little bit deeper into the actual types of macroinvertebrates within those watersheds. So this graph here is showing you relative abundance of the 5 most common taxon that were found in the stream over time. So you can see the forested site has a diversity of these 5 taxon, whereas the treatment watersheds transition from having a diversity of species of taxon to being dominated by a single tolerant taxon. If you're not familiar with the scientific names, there's some of the common names, and a loss of these sensitive taxons. So while the benthic assemblages may be somewhat protected when you look at IBI scores, when you dive a little deeper and look at the taxa, those sensitive taxa may not fully recover after development, even though our IBI scores are telling us that the stream is still in good condition. When we dive down into the actual critters that live in the stream, it's giving us a better picture of what's going on. So, it's kind of a loaded question, but can using this green stormwater infrastructure save our suburban streams? Is using more distributed control the solution? It provides a lot of benefits in terms of hydrology. So we're able to attenuate peak flows and runoff volumes, but we still have those really large storm events that we don't have capacity to manage. It can also improve water quality, especially for sediment. But we still have, issues with things like stream bank erosion because of those large events that we can't manage with the storage that we've created on the landscape. And can also, maintain stream health to some extent, but this is suggesting that the construction phase of development is really important in terms of preserving the communities that live in the stream, because we saw those declines in the Benthic community happening during construction within the watersheds. So just thinking about, what's next, what are some other things that we're trying to better understand and learn about in the future. What goes in our streams must come out, right? Stormwater has to go somewhere. We have to do something with it. And one of the big unknowns that we're thinking about now is what's happening to these contaminant cocktails and emerging contaminants within stormwater. There's a USGS study that came out in 2019 that looked at contaminant mixtures, so the types of contaminants found in stormwater. So these are all different sites here. Most of them are in the Midwest or California, and the number of organic chemicals that were detected in stormwater samples, and then the types of chemicals that were detected. So pesticides were the most common group found within the stormwater in these samples. And the median number of chemicals that were detected in the site was 73 different chemicals. So these, all of these chemicals, while they're detected in our stream, in these samples, they're very, very low concentration. So even though, these chemicals were detected, they weren't really high concentrations. You can also look at chemicals in the stream themselves. So USGS did a study of streams across the Piedmont in the southeast, including Charlotte and Raleigh, Durham. And we can look at within the stream water itself, not just the storm water, but the actual stream water. This is showing you different pharmaceuticals that were found in streams in North Carolina. So each of these bars here shows you one stream, and all of the different chemicals, the number of times that chemical was detected. So the more red it is, the more chemicals were detected. And you can see pharmaceuticals that were most commonly detected were anti-diabetic medications, tobacco byproducts, and caffeine. And these three watersheds here stick out as having a lot of different types of pharmaceuticals within the streams themselves. If you know these three streams, Ellerby Creek, Mill Creek, Morgan Creek, Chapel Hill, they all have wastewater treatment plants upstream. So most of the streams with wastewater treatment plants had more types of pharmaceuticals detected. And again, these were detected, but they were in low concentrations. Let's also look at pesticides. So here's just some common pesticides that were identified across those same streams, frequently found across all of the streams that were sampled. So just to kind of provide a summary of what I've talked about today, distributed stormwater control can minimize impacts, but it seems like the construction phase of development is pretty important in understanding, when degradation might be occurring, and that the amount of impervious cover, not just, the type and density of stormwater practices that are in the watershed, seems to be an important factor in predicting if the Benthic community is able to rebound, and that more practices and more distributed control isn't necessarily better. It's really important to think about how those practices are connected and configured on the landscape, and that takes a lot of data and information if you want to understand these changes in watersheds, where they weren't necessarily constructed to answer these questions. It takes a lot of effort to compile that information and get an estimate of how much storage there is. And then emerging contaminants seem to be increasingly important, but their impacts are pretty much unknown. A lot of these streams, we don't know what impact that has on the biotic communities that live in the stream, and also, a lot of our water sources are coming from streams and lakes in the area. So, we don't know how much that's impacting the sustainability of water resources into the future. So something to just think about in the future. And thanks for listening. And if you have questions, you can type them in the chat box at the bottom. Put my email address, and if you're on Twitter, you can follow me. I tweet about streams and rivers and gardening and all sorts of things. So if you're interested in knowing more or want more details about anything, you can shoot me an email, and I'm happy to provide you with a little bit more information. So thanks. I think we have a little time for questions. Not sure how you want to handle questions, but if you type them in the chat, I can answer them as they come in.
Yeah, thank you so much, Krissy. This is Anna Martin coming in. I think our moderator today is Frank Lopez from WRI. So Frank, if you are on, I'm going to let you come in. We do have some questions coming into the chat. So Frank, if you want to take it away.
Thank you, Anna. Krissy, great presentation. Thanks for providing that information. So there are a couple of questions in the chat, and one of them early on was related to publication. Are there results of this research in an article that you could share with us? And if so, you know, we could certainly put it in the chat box so people could find it.
Yeah, we have a project website that has all the publications on it, so I can put a link to that in the chat box. So you can go there to find publications related to this work. I'll just pop it in there. And if you can't access any of them, I can email you a copy if you don't have subscriptions to different journals. Oh, I think I just sent it to one person, sorry. There you go. There's a tab for publications. Am I sharing my screen? I don't think you can see what I see.
A couple other questions in here already. Your presentation seems to have struck a chord and created some interest. So one of the questions from Steve Anderson is would you expect increases in ion loads in the south where salting is not common? If so, what are the most common contributors? And the multi-part question here: do you think the decline in macroinvertebrates diversity is due to increases in conductivity ion loading, since you continue to see lasting impacts in treatment watersheds after in the treatment watershed after construction, or is it increased flow? So you know, I can back that up and ask you that in pieces if you'd like. But first question is, would you expect increases in ion loads in the south where salting is not common?
Yeah, so actually one of my colleagues, Rosemary Finelli, she actually looked at specific conductance patterns across the southeast and up to the northeast, so kind of a gradient of road salting. And I think she did find, in a publication that recently came out this year, they did find some increases in conductance in streams in Atlanta, but not as high of an increase as, you know, streams up in the northeast where, yeah, salting is much more common. So some other contributors, you know, in cities could be things like concrete weathering, where you have, you know, a lot of concrete that's going to contribute ions to the stream. So there's other sources besides salt, you know, that are contributing to those increases in other cities where you have less salting. I guess the other question was, yeah, is a decline due to, you know, what's causing the decline? I think it's more related to sediment. So we actually have some information about particle size distributions and how the distribution of particles within those streams has changed. And we saw an increase in fines and sand during construction in that watershed where the Benthic Community declined and then rebounded. So sand, you know, having a lot of fine sediment is going to bury the macroinvertebrates, their habitat. So even though the construction had sediment erosion control facilities, we still saw a change in the distribution of particles, you know, that increase in fines and sand in the watershed. So I think, you know, it's a combination of things. It's not just one factor, but I think that at least in terms of like the most immediate impact, that shift in having more fines and sands seems to be something that might have led to that decline. And then, yeah, we don't really know what the lasting impacts are. You know, we're still, you know, the county's still collecting data, and we're still working with the county to understand those patterns. So we should be able to look at, you know, what happens in these other watersheds over time. It just takes a long time to get enough information to make a conclusion. So it just kind of shows the value of having these long-term data sets.
Thank you, Krissy. The next question is also from the chat. Do you think that watershed storage capacity could better approximate the forested conditions using so-called on-site management practices that accept, infiltrate, and store precipitation, such as permeable pavements, green roofs, and soil preservation amendment? I wonder if widespread use of these practices could manage most stormwater before it gets into gets into concentrated flows and goes to offsite practices like bioretention, wetlands, etc.
Yeah, I think that definitely having more storage would be beneficial. I guess, one of the problem with these smaller facilities is that they're still not going to be able to manage those large events, which are kind of driving the increases in peaks, which leads to more stream bank erosion. So it's kind of, this balance of what density and what type of practice and how much storage you need to, create enough storage to minimize the impacts. And, it seems like they're getting closer to, at least in that treatment one watershed, closer to, kind of that balance, but it's not quite there. Still losing those sensitive species. So, since I was saying that construction phase seems to be important, if we're able to better manage sediment during construction, maybe we would have been able to maintain some of those sensitive taxa, and they would have maybe have been able to rebound to a better extent in that watershed after development. Since we're seeing, some of that, those taxa are still there, but they're not there at the numbers that they were before. So I don't know that putting more stormwater practices in there now would be able to bring those, communities back. But if we're able to manage the construction phase and also put in, these types of practices in this high density, we might be able to provide more of a impact for the community and the communities. But yeah, and green roofs, it depends on the type of house you have. So the roof pitches here wouldn't allow for a green roof probably, but some of the other practices and soil preservation and amendment definitely is something that would be beneficial. If you just look at the scale of changes that happened in this watershed during construction, like how much earth was moved and valleys were filled in and grades were leveled, it's pretty massive earth movement. So if we can minimize some of that grading and maintain more of the buffer around the stream, that's one of the differences between those two watersheds. If you look at just how much buffer there was, you just kind of see here. There's a bit more buffer in the treatment one watershed compared to the treatment two watershed. So the house is kind of encroached pretty close to the stream in the treatment two watershed, whereas there seems to be a wider buffer here. So maintaining those buffers, and this also just has to do with like what the landscape looked like before. There wasn't a lot of buffer here down by where the Benthic Community is actually monitored in the treatment two. It was agricultural fields. So, maybe more reforestation in that area and planting trees and protecting that zone. The buffer was protected here too, but it's, a fairly narrow buffer.
Thank you, Krissy. Next question is one related to stream morphology, and it's from JV from the city of Durham. How have the stream channels in treatment 1 and 2 watersheds changed since being developed? Are the treatment 1 and 2 stream banks eroding at a rate when they were agricultural, or the stream bank erosion increased since development?
great question. I'm just in the geomorphology, the part I didn't talk about, JV. Yeah, so we actually have been looking at changes. So each of these watersheds also has monumented cross sections that have been surveyed annually for the last 20 years too. So we can look at things like stream bank erosion rates before and after development. And so we're actually working on analyzing a lot of that data right now and writing it up. But in general, these streams were impacted by agriculture previously. So, they were already in size before the subdivisions went in due to the agricultural history. So even the forested watershed, some of the banks there are over my head. It's not a natural stream system anymore. It's modified. It's hard to find a natural unhuman altered landscape anymore. But we can look at those rates and changes, and we are still seeing substantial stream bank erosion in certain parts of the watershed. If it's more than what it was previously when it was agriculture, I don't know the answer to that question yet, but we are seeing substantial bank erosion in these streams still, even with the stormwater facilities that we have because of those really big flow events. And there's been a lot of really large events that have happened in the last few years in this area. So, as we're having more intense precipitation events, we're having more peak flows, more shear stress to erode those channels. So we're still seeing a lot of erosion. But it probably would have been even more erosion had there not been, all of these stormwater facilities built upstream. So while we're seeing erosion, it's probably less than it would have been if there would be no stormwater practices themselves.
Thank you. Next question is related to how communities can use research like this. So how can your research be used to help municipalities put more effective management practices in place, likewise for more effective controls during construction?
Great question. Yeah, so this is a really unique area. So Clarksburg is the county has designated this area as like a special protection area. So they require developers to mitigate 100% of the impervious cover in each of these, in this area. Because of that, they want to maintain the health of those streams in this area because they are high quality still. And, this is the kind of type of stormwater facility that they envisioned would have the best impact. So they require the developer to put in these practices here. So that's not the case everywhere. It's not required. It's voluntary, or maybe not to this extent. So Clarksburg is kind of the ideal, optimal sort of place to start asking these questions to better understand what's going on. And so it can provide some insights on, what happens when we do this type of management. The neighborhoods look pretty similar to like a neighborhood here. They just have, these detention ponds and sand filters in the backyards of some of the people. So in some people's backyards, most people probably don't even realize that, who live here, that this is the arrangement of stormwater practices. I doubt it. I saw kids using the dry ponds as like sledding. They were sledding down the banks of the dry ponds. So it's kind of like a play space for kids in the neighborhood. So I guess in terms of, what other places can use this information, just kind of understanding that it can be beneficial for hydrology and mitigating the impacts of peak flows and runoff amounts and water quality to some extent. But, you know, there's all these combinations of stressors that are impacting the Benthic community. So it's hard to pinpoint and, you know, take what we've learned here and, you know, assume that everything that we learned in Maryland would apply to, you know, some city in North Carolina, for example. Some characteristics, you know, the nitrate concentrations aren't that high here, right? 6 milligrams per liter is pretty high. So some of these patterns, you know, you might not see in North Carolina. So when we have multiple study areas where we have this arrangement of facilities, if we can ask the same question, do we see similar patterns, you know, for a neighborhood here in North Carolina that has a high density of stormwater facilities like this? So that's something I've been trying to work on in the last few years since I moved to North Carolina, to, you know, start looking at some of these patterns and streams here. Are there any places where, you know, we have this type of novel stormwater management that we could monitor and ask these questions? It just takes so long to develop those long-term data sets to look at change over time in one place, which is kind of the ideal monitoring arrangement. So yeah, we need to be better about communicating how, you know, these results could be used for practitioners and people at the county and cities. So we're working on writing some like fact sheets that kind of summarize some of these results in more like public friendly language that we could post on our website, rather than just, you know, pointing to a publication or a paper. Which, like, nobody wants to read like a 20-page scientific paper probably. So trying to distill it down a bit more. And then we're working on like a synthesis paper that has lessons learned from the monitoring. So kind of distilling it all down into these concrete, you know, one statement sentences about what's happened. So that should be coming up in like the next year or so. I've been working on that this year.
Thank you, Krissy. I don't see any questions in the chat. What I'm going to do is I'm going to pause and give everybody an opportunity to either raise a hand or just hop on in and ask a question. But if I pause and don't hear anything, Krissy, I'm going to ask you a question about, you know, your future research directions and questions that might have come from this work that you'd like to explore a little bit further. But I'll pause and see if anybody wants to hop on in. Jason had a comment here. He might want to expand upon that, for example.
Did you want me to answer your question now, or?
I wanted to see if anybody from the audience wanted to ask a question and give them an opportunity before I hopped in.
Okay, and Jason's comment was something about
the cost of decentralized systems as opposed to centralized treatment.
Okay, yeah. We've seen that centralized would continue to be most cost effective. Yeah. Yeah. I guess if you're just looking at treatment of sediment or something, but you could also think about those distributed facilities as having other sorts of benefits as well, not just sediment. So increasing green space, you plant more trees along the roadways, and these tree box filters and infiltration trenches and things, you know, does that contribute to increases in property values for the houses, and also you know, reducing things like urban heat island and these other factors that are harder to quantify in like a value. So yeah, when you're thinking about just total volume and sediment, perhaps centralized is the most cost effective, but you know, if you add up the additional benefits provided by these smaller facilities, do they provide more value overall? It's kind of a remaining question.
So my question is you know, where's your future directions? Where's the research taking you, and what questions would you like to examine, going forward from this effort?
Yeah, so we, my office, now, we have a pretty good group of urban folks. So we're trying to do more urban work in North Carolina and in the Piedmont here around Raleigh. So we're starting to think more about stream bank erosion and how we can look at how that's changed over time using existing data sets like LiDAR to look at topographic changes where we have repeat LiDAR data. So can we use LiDAR to map changes in bank erosion? This is working with some folks at NC State too, Barbara Dahl, to think about how, can we broadly map hotspots for stream bank erosion across the whole city to provide information that can be used to better target stream restoration and stabilization projects. So that's something that we're going to be working on in the future. In the near term, I guess longer term, I'd like to, do a similar sort of monitoring study to Clarksburg, somewhere in North Carolina. Maybe not on quite the scale, but is there a neighborhood or a street where we could implement these practices and look at changes in hydrology and water quality before and after kind of like a street scale project was implemented. So things like that have been done in, Ohio and up in the Great Lakes region, but not a ton of the sort of neighborhood scale work has been done here. And then also my office is in Atlanta. It includes North Carolina, South Carolina, and Georgia. So we have a pretty large urban monitoring network in Atlanta. So trying to work more with folks in our Atlanta office to get a little bit more value out of existing projects or existing data sets that we already have that maybe we haven't analyzed in a way that we could target that information to look a little bit more at stormwater.
Thank you, Krissy. I'm going to wait a couple more rounds here and then see if anyone wants to hop in. And if not, I'm going to hand it back off to Daniel to close us out.
Great, sounds good.
Not seeing any hands up. Krissy, I'm gonna hand it back to Daniel. Thanks so much for the presentation.
Yeah, thank you.
While we're waiting on Daniel, this is Anna Martin again. I want to thank Dr. Hopkins for being, I lost my video, for being here to present today. Thank you so much for all the information you provided, Krissy. I'm sure the audience was here for most of the time today, so very engaging. I hope they got a lot out of it. And again, we've put your email address into the chat box, and I know it was on your last slide. So this recording will be available soon. We are going to have it closed captioned, and it'll be available on the NCWRA website. That usually takes a little bit of processing time, so please be patient. If anyone needs an immediate copy of it, I do have something I can share. It will not be polished, but it'll be viewable. So again, we just want to thank our audience, and I've also put the link to the, excuse me, the survey for today's webinar in the chat box. So please do provide your feedback and ideas for future forums. Those are always super helpful for our program committee to meet your needs and to make sure that we're meeting your expectations for these forums and the educational opportunities that are available. Bringing you the latest updates and stuff you're actually interested in is part of our job. So we want to make sure we're hitting all those key points. I will just mention briefly too that hopefully NCWRA will be back in person coming this fall. Our next scheduled forum will be in September in hopefully the McKimmon Center, back at the old stomping grounds for those of you who have been there before. So again, it may be a little different. We may be spread a little further apart, but that is our hope. So I see Daniel has come back on, and Daniel, I will let you close it out with any other announcements or things that you wanted to mention.
Thanks there, Anna. No, there's not much else. I just wanted to say again, thank you so much, Dr. Hopkins, for presenting this. This is definitely some great information and something that I think a lot of us are going to be chewing on now, you know, looking at green infrastructure and its prevalence and growing prevalence throughout the country, and especially hopefully within North Carolina. So with that, I thank everybody. And I hope everybody remembers to renew their membership. And again, reach out to the NCWRA board or contact us on the website if you have any questions, concerns, suggestions. We're always open to feedback. Thank you.